Lesson 1, work. One of the difficulties here, and I mentioned this already, is the word work in English has a very different meaning from the word work in physics. Fritz, in physics, you do work on an object. When you do work on an object, you've changed that object's energy state. You've either given it energy or you've taken energy away. I haven't defined what energy is. We're going to do that. Energy, by the way, is the ability to do work. So it's kind of a roundabout definition, but we're going to get there. There's going to be 3 different ways to find work, 3 definitions. The first way is the easiest and cleanest, but it only works in certain situations. The second method is a bit longer. The third method is something called the work energy theorem. It's the best one, but it's also by far the most cumbersome. It's the biggest pain to use. So we're going to start off with the cleanest definition today. It says this: if work is to be done on an object, 2 things must happen. Number 1, you must have a force acting on the object. And number 2, the object must move. More specifically, the object must move through a distance in the same direction as the force. If you're pushing an object to the right and it moves up, no work has been done in our physics definition. If you're pushing an object to the right and it moves to the right, work has been done. Work is a scalar, and it's calculated by, can you find the W equals equation on your formula sheet? Just so you know, it's on the front page about 2/3 of the way down. That's the work energy section. Those couple of lines there are what we're going to be spending about 3 weeks looking at. Ryan, work is what times what? Yep. Force times distance. I think on your sheet I didn't bother putting the times symbol in. So Ryan, what would the units be for work? What do I measure force in? What do I measure distance in? So technically, work is measured in Newton meters, but the concept of work is very important. It's so important that we've taken this, the Newton meter, and we've given it its own special name. Work is measured in joules, symbol capital J, named after a scientist whose last name was Joule. 1 joule of work is if you apply a force of 1 Newton to move an object 1 meter, you've done 1 joule of work. 1 joule of work is pretty small. Most of you can do 1,000 joules of work, and depending on how fast you're doing it, probably not even notice that you're doing it, carry on a conversation with your friend absent-mindedly, and not be aware of the fact that you're doing work. If I make you do it fast, sprinting, okay, fine. There's a condition here, though. So work is force times distance. The force and the distance have to be in the same direction. And there's a second condition here. The force has to be constant. This becomes a problem next year when we start looking at rocket science, when we start putting satellites in orbit. Because as you move further from the Earth, further and further away, what happens to the force of gravity? It's not constant. It gets smaller and smaller. And so unfortunately, to do rocket science, hey, it is rocket science. You can't just go force times distance. To figure out how much work to put something in orbit, it'll be the single longest question you do in all of Physics 12. It takes up about 15 lines. It's an entire page. It's the joke I'll make next year. It's a lot of work to figure out how much work to put something in orbit. And you also get a really, really big answer, which explains why it's so stinking expensive to put something in orbit. Example 1. I like example 1. I like example 1. Example 1 is the next question. How much work does it take to lift a 12-kilogram mass from the ground to a height of 9.5 meters? I would like you all, please, to underline the word lift. And what we're going to do is we're going to generate a work equation when you lift an object. Now, it's going to start out as force times distance, but we're going to modify it. 12 kilograms, by the way, that's about the same as the big lead weight in front of Ben sitting on the desk there. Don't touch it. 9.5 meters. I don't know if you remember when we did the little lab in the back stairwell where we were dropping objects and timing it. We measured the distance to that top railing. I think it was 4.5 meters. So basically think to yourself 2.5 flights of school stairs. So these stairs behind me would be considered 1 flight. 2 of those and a bit more. You know what? All of you could carry that up the stairs, and you wouldn't be moaning and groaning. You might notice it, but honestly, if we did it right, you could certainly carry a conversation on with a friend of yours. If we were doing it slowly, if I wasn't making you sprint, this is why I keep saying work is not tiredness. How fast I make you do work, that's what makes you tired. If I made you sprint up the stairs, you'd get tired. But if you were walking it, Kira, there's not a single person here who I couldn't say, could you carry that up 2 flights of stairs and give it to so-and-so? Yeah, I could. Which force? Which distance? Well, this is a job for a free body diagram. Let's assume that we're lifting it at a constant speed. We're not speeding it up or slowing down. We're doing the minimum work required. What are the forces acting on this object as we lift it? Get the obvious one. Yep. If we're at a constant speed, what can you tell me about the length of the arrow pointing up? It will be identical to the length of... So I'm going to draw an arrow pointing up, and I'm going to call it F lift. And I'm going to say that lifting something, the work done when you lift something, is the force of the lift times the distance that you lift it. So if you can fit in 2 little subscripted lift. Now, when you're lifting it up a vertical distance, we call that a height. So if you can leave a space and put a little lowercase h there. Now, right here, I should put the force that I use to lift it. I don't know the force that I use to lift it. Oh, but look. Another force the same size as the force to lift it. If I'm lifting it at a constant speed, what's the force that's the same size? The work done in lifting an object is mgh. Now, if you want to, you could add that to your formula sheet. I'm going to say hold off. Look at your formula sheet right now. I think there's an mgh there already. You see it, Kedra? But what did I say that was? I didn't say that was equal to work. I said that was equal to phys ed. No. The PE stands for potential energy. When you lift something, you're giving it energy. I told you when you do work on an object, you're changing its energy state. You're storing energy in it. And the reason I know you're storing energy in it is if I let it go, it'll move on its own. The only way it can start to move on its own is if it's got some stored energy. Okay? So this sort of starts to explain one way of thinking about why when you let go of an object from a height, it drops. One way to think about it is there's an unbalanced force acting on it, but another way to think about it is it's got some energy to burn. And it's going to turn it into motion or kinetic energy. Some of you in Science 10 last year, if your Science 10 teacher was doing the new curriculum, you may have talked about kinetic energy and potential energy. Last year was the transition year. Your Science 10 teacher might have been doing the old curriculum where the physics component was acceleration and velocity and time and distance and displacement. I think if you had Miss Brar, I think she did the new curriculum, and I think some of the other Science 10s did the different one. So anyways, both of them suck. They're done terribly in Science 10. It's not the teacher's fault. The textbooks are set up terribly. I railed against it. I'm going to teach it to you properly. For example, you're supposed to teach them energy in Science 10. Energy is defined as the ability to do work. So you're teaching them energy, but you don't teach them what work is. Oh, you can't do that. So you can decide if you want to add this equation, work done by lifting is mgh, or you got an mgh on your formula sheet. You can decide whether that will be your trigger. I would say, Logan, hold off and adding it on your sheet. Don't clutter it up yet. And if you find a week from now you can never remember how to figure out the work done on lifting an object, well, then add it. But I think you'll have it by then. What's the mass? 12. G, 9.8. Not negative because it's a scalar. H, the vertical height, 9.5. By the way, notice that the force of lifting and the distance are in the same direction, Dustin. I made sure of that. This is going to be a little less than 1,200 because this is almost 12 times 100. It's going to be 1,100 something. What do you get? Yeah. 1117.2. And I'd probably write that as 1,120 joules if it was multiple choice. Units, joules. Okay. So all of you can pull off about 1,000 joules of work. Your homework's going to be every question. Cole pushes, you know what? Kyle, could you stand up, please? We'll use Kyle instead of Mystery Human Cole. Could you walk against the wall over there? And could you push with 2 hands against the wall as hard as you can? Kyle pushes against a brick wall as hard as you can for 12 seconds. 1, 2, 3. Okay, you can stop, but just kind of freeze the pose. Amazingly, the wall does not move. Now, if I made Kyle do that for an hour, would he get tired? Yeah. Is he doing work? Why is he doing no work in the physics sense? How do we define work? Work is what times what? Is he applying a force? The wall isn't going, it's nothing to do with Kyle. The wall isn't going anywhere because you do work on an object. Is he doing any work on the wall? No, he's applying a force, but it ain't moving. He's not changing the wall's energy state. Thank you, Kyle. You can sit down. Work equals 0 joules. If you want to make a little note, no distance. Would you have gotten tired if I made you push and strain for an hour? That's not work, not in physics. I don't care about tiredness. I care about changing an object's energy state. Now, if you do push something and it moves, you can figure out how much work is done. Pushing a box along the floor requires a steady force of 22.5 newtons. If you push it for 13.6 meters, how much work have you done? I'm imagining that we're pushing a box, pointing it to the right, and it's continuing going in a straight line. So I think the force and the distance are in the same direction. I think I can go straight to force times distance. The force is 22.5. The distance is 13.6. What do you get? (306 joules of work. That you would shrug off. Again, if I made you do it while sprinting, your heart rate would briefly go up. But if I said, yeah, just do this casually and spread it out over 30 seconds, not only would you not break up a sweat, you probably could do it absent-mindedly while just chatting with a friend. And just with this definition, work equals force times distance, we can explain one of these Captain Obvious things that you have all picked up as a child. We can explain why it's the case. Is it easier to ride up a steep hill or a shallow hill? Someone said it. Shallow hills are easier to bike up. Why? So I'm going to assume all of you have tried or have actually biked up a hill. And you probably noticed, if it's steeper, I got to push harder. I got to exert a bigger force. Why? Okay. Dylan pedals his bike up a 19-meter high hill that's 91.4 meters long. The combined mass of the bike and rider is 65 kilograms. The bike requires a steady force to continue up the hill. If I wanted to figure out how much work to get to the top of the hill, don't write this down. Let's try that again, Mr. Dueck. Why can't I go the force of gravity times 91.4? What direction is the force of gravity? Vertical. So I have to use a distance that is likewise vertical. If I want to calculate how much work to go up the hill, the work is going to be mgh. So I wrote here, suppose Dylan strapped the bike to his back with like bungee cords or something, and he used a rope to hand over hand climb to the top of the hill, up the backside of the hill. How much work will this require? I can use mgh because this distance here is in the vertical direction, and I can use mg because that free body diagram that we drew, we said the force of the lift, I don't know, but look, it'll be the same size as mg. So this is how much work it's going to take Dylan if he wants to climb to the top of the hill. It's going to be 65 times 9.8 times 19, which is what? 12,103 newtons. By the way, the only way he can do this is if he's capable of pulling up with mg. Yeah, newtons, joules, Mr. Dueck, joules. Thank you, Abby. The only way that Dylan can do this is if he's capable with his hands of exerting mg. Can you quickly calculate mg? What is 65 times 9.8? Okay. How much work will Dylan do riding up the hill? The answer is 12,103 joules. It doesn't matter whether he goes straight up or whether he spreads it out over a longer distance. The amount of work he's going to do is going to be the same, because when you ride up a hill, which force are you doing work against? Gravity. And so which distance should we use? A vertical one to match gravity. So how much work does he do riding up the hill? 12,103 joules. How much force does he exert if he hand over hand climbs to the top of the hill? 637 newtons. What about if he's biking up the hill? How much force does he need to pedal? Part B. Sorry, how much force does he need to pedal up the hill? Kira, what's part C asking me to find? Calculate the? Now, F equals what? MA, I'm not going to use that. There was also a force in the impulse equation, not going to use that. Here's yet another definition of force. And I'm going to use, what did we find in part A? What does the W stand for? Four-letter word, starts with W, ends in a K, has an O and R in the middle. What? Is there an equation for work that also has a force in it? Psst, look at your green sheet. Get the F by itself, please. Divide what over? Okay. Here is another way to calculate force. If I know how much work was done, and I divide it by the distance that we performed that work over. Now, here's what I want you to notice. As the hill gets shallower, what happens to the distance of the hill? Longer or shorter? Use your imagination looking at the ramp there. As this gets bigger, as the hill gets shallower, D gets bigger, and the pedaling force required to make it up the hill gets smaller because you're dividing by a bigger number. As the hill gets steeper, what happens to the length of the ramp? It gets shorter. In fact, if it was dead vertical, I can tell you exactly how long it would be, 19 meters. If it's just off of vertical, it's going to be like 19.2, 20. The shorter it is, which means it's steeper, the bigger this force will be because you're dividing by a smaller number. That's why it's tougher to ride up a steeper hill than it is a shallower hill. So if he was hand over handing it, he'd have to be using 637 newtons. Here, it's going to be 12,103. Because now I'm riding up the hill, I'm going to use that distance there, 91.4. Sorry, what? 100.4, I think, yeah? I didn't do that in my head. I remembered it. Way smaller force. So what we say, the ramp is what we call in physics a simple machine. What does a machine do in physics? It's not a bunch of robots and gears. A machine is a force multiplier. A machine allows you to accomplish a task with less force. A machine makes you stronger. To try and lift this straight up, most of us couldn't do. Build a ramp. The Egyptians built the pyramids, we think, without the wheel, but they used ramps. And by building shallow ramps, instead of having to lift those bricks straight up, they increased the distance. They did the same amount of work. The trade-off is if you increase the distance, you lower the force, but you increase the distance. You got to push them for further. What was the height here? What was the height here? What's the height here? 12,000, what was it? 103 joules. The beauty of work being a scalar, it doesn't care about the path you use to get there. All it cares about is what's the direction of the force that you were doing work against, vertical. Well, then give me the vertical distance and shut up. Okay. If I made this angle smaller, 6 degrees, you'd have a much longer ramp. D would be bigger, F would be smaller. You get the same amount of work. The ramp, one of the probably top 5 inventions of humanity. Hey, what takes more work, lifting a 25 kilogram mass to a height of 4 meters or lifting a 50 kilogram sack to a height of 2 meters? Well, let's crunch it. The work for the first object is going to be, well, the key word here, can you underline the words lifting and lifting? It's going to be, how do we calculate the work done by lifting an object? MGH. So this is going to be mass 1, height 1. It's going to be 25 times 9.8 times 4. Actually, I don't need a calculator for this. What's 25 times 4? This is 100 times 9.8. I think it's 980 joules of work. What was that? Yeah, if you crunch the second one, you get a 50 here, 9.8, and a 2 here. Again, you get 100 times 9.8. They are the same. It's a bit of a trick question. Okay. Work is what times what? It's force times distance. The force and the distance have to be in the same direction, and the force has to be constant, not changing. Okay. What if the force is changing? There's a second definition of work, Matt. You can make it? That was a good yawn. There's a second definition of work. So if you have a changing force, work is also the area under a force versus distance graph. How will I know when to use that one, Mr. Dueck? They'll give you a graph. Okay? So don't overcomplicate that one. If I can, I'll try force times distance if they give me numbers. They give me a graph. It's a force versus distance graph. It's going to be the area underneath it. So this question here says, how much work was done in moving this object from 2 meters to 5 meters? First thing I'd like you to do, please, is do a little dotted line at 2 meters, a little dotted line at 5 meters, and then put your pencil down for a second once you've done those dotted lines. I'm going to color this in. I'm going to recommend you don't. The area we're talking about, though, is this one here. That area will be the work done in moving this mystery object from 2 meters to 5 meters. That area, don't write this down, has this shape here. 2 parallel sides and 2 sides that are not parallel. Does anybody know what we call that shape? It starts with the letter T. TR. It's trapezoid. Who said that? Fritz? Okay. There may be a candy for you. We'll find out. Does anybody here know the formula for the area of a trapezoid? There is one. It's obscure. Everyone, no, they teach it in Europe. If I have an exchange student, they'll often know it. So in my Block D class yesterday, my exchange student knew it. And he politely asked me if he could use it. Yeah. No, okay. There's a reason we don't bother teaching it. It's redundant. What does redundant mean? You don't need it. It's nice because you can do it in one line, but you don't need it because any trapezoid ever can be broken up into a rectangle and a triangle. And those two, you do have equations for the area of. You have been taught the formula for the area of a rectangle, and you have been taught the formula for the area of a triangle. Pick your pencils up. So if you'd be so kind as to put a little dotted line right there, put a big 1 in the rectangle, and a big 2 in the triangle. I have tried to draw every possible permutation of trapezoids, Abby, that I can think of, and I couldn't find a single one that I couldn't break up into a triangle and a rectangle. So do that. If you want to know the area of a trapezoid, ask me later in class or see me during flex. It's a cool equation. Area 1, what shape is that first area? Well, it's a rectangle. What's the formula for the area of a rectangle? Now, if you don't know this, and I mean right away, you may want to add this to the bottom of your green sheet where you have the 3.6 conversion from meters per second to kilometers per hour. You may want to add this. I think you should memorize this, but this year I'll live with you having to look at your formula sheet. What's the formula for the area of a rectangle? Yeah. If some people write length times width, and I will give you full credit for that, I'm going to go base times height, which is the same thing, but you'll see why for a reason. I'm going to write it as that. How long is the base of this rectangle? Please don't say 5. Look at the numbers carefully. How long is the base of this rectangle? 3. What's the height of this rectangle? Please don't say 2. Look at the scale. Please don't say 1. Oops, gave it away. Look at the scale carefully. It's 2. Yes, because each square is worth 2. Oh, by the way, Ryan, at 2 meters, how big is the force in newtons? Read across. Read across. Say it again. At 5 meters, how big is the force in newtons? Is that a constant force? That's why I can't use force times distance. So don't just go, oh, 8 times 5, 40. I have to find the area. In your head, 3 times 2? Good. Now we're going to find the area of the triangle. Does anybody know the formula for the area of a triangle? I'll look at Dan if he's got that. Do you have it? Any triangle is half of a rectangle. And that's why I typically do the rectangle as base times height, and then I just remember triangle is half of one of those. It's base times height over 2. If you don't know the area of a triangle, you might want to add that to your formula sheet. I wouldn't call them A1 and A2. I would call them either area rectangle. You know what I would do? Capital A and then a small shape of a rectangle equals base times height. Capital A and then a small triangle equals BH over 2. Looking at this triangle, what's the base? Still 3. What's the height of this triangle? Don't say 8. 6. Divided by 2. Oscar, what's 3 times 6 divided by 2? Yeah. That was so over his head. Wow. 9. Yeah. 9. Yeah. Not wow. Boy. Yeah. 9. Jeez. Really 9 you. In your head, Oscar, 6 plus 9. Now think about what we just did. We were able to figure out how much work to move this object. We don't even know the object's mass, but I can tell you how much work it took. That's not bad. Oh, if I know the object's mass, I can even tell you how fast it's traveling, and that'll be a couple lessons from now. If I know how much work was done, that's some very useful information, whether I get it through force times distance or whether I get it through the area underneath the force versus distance graph. So we have 2 definitions for work. We're going to learn a third one in a couple of days. But the first definition is force times distance, but this requires a constant force, and the distance have to be in the same direction. The second definition, work is the area under a force versus distance or displacement graph. That one will be fairly obvious because, oh, they gave me a graph. If I give you a graph, it will be one of 3 shapes. It'll be a rectangle, it'll be a triangle, or it'll be a trapezoid. Probably a trapezoid because that contains within it both a rectangle and a triangle, but not always. Example 8. How much work was done moving this mystery object 10 meters? Well, it's going to be that area right there. Is that a rectangle? Is that a triangle? What shape is that? I'm going to break it up into a rectangle and a triangle. Area of the first shape is going to be length times width, or base times height. How long is the base? Looks like 10. What's the height? I think 20. And we're getting that, William, just by reading across and reading down, right? (200 joules). Area of the triangle is going to be base times height divided by 2. The base, again, is 10. The height, not 30. What's the height of that little triangle there? 10. Divided by 2. Pretty sure that's 50. How much work was done? 250 joules of work. Tell me VI and the mass. I can now tell you VF. Example 9. Let's kick it up a notch. A box, 124 kilogram box. 124 kilograms, that's about 300 pounds. This is big. It's being pushed along the floor that has a mu, a coefficient of friction, of 0.25. The fact that I see a mu, I'll bet you this is a job for a free body diagram. The person pushing applies a force of 525 newtons. I bet you that's F applied, because they said applies a force over a distance of 22 meters. Cool. Cool. Dustin, what's A want me to find? What's B want me to find? No. What's A want me to find? You said the work. What's B want me to find? I think the work. What's C want me to find? We need to, I guess, be more specific. So let's start over. What does A want me to find? Read the whole thing out loud, please. The work. What force is the person pushing? The applied force. You know what? I think A wants me to find the work done by the applied force. Okay? Over here, let's do a free body diagram. Here's the box as a dot. Dustin, what are the forces acting on it? Get the obvious one. Yeah. Is it sinking into the ground like quicksand? Is it flying through like Superman? What else? Normal force? Yeah, you had no effing clue. Let's assume we're pushing to the right. So F applied, and I can even tell you how big it is. 525 newtons. Which force am I missing, my friend? Mu's not a force. What? Friction, which way? Pointing. Yeah, bigger, small, you know what? I don't care right now. I'm just going to make sure I don't forget that there's some friction there. Okay. So, work equals what times what? Our new equation for today. So I think the work done by the applied force is going to be the applied force times distance. Let me do a quick check. We're pushing that way. Which way is the box moving? Also that way? Are the force and the distance in the same direction? Hey, we're good to go. 525 times 22. How many joules of work were done on this box? $11,550. right, folks? Okay. However, now we're going to be a bit more accurate. Not all of that actually went into making this box speed up as you push on it. We lost a lot of that energy to friction, mostly as heat. You can actually try this right now with your non-writing hand. If you press down hard on your lab desk with your left hand or your non-writing hand, and then you pull towards yourself really quick, you'll generate enough heat if you press down hard and pull quick. You can actually burn yourself. There's a fair bit of energy loss here. Okay? So, don't burn yourself badly, but there's a lot of heat there. Okay. Logan, what's B want me to find? Work? Yeah, more specific. So I think the work in overcoming friction is going to be, correct me if I'm wrong, Logan, the force of friction times distance. Seems to be kind of symmetrical that way, yes? Friction is what times what? And then tuck the D in. I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. Which one? Yeah. So if I want to find the force, the work done overcoming friction, it's going to be M times G times D. That D, by the way, is not an H. Don't think, well, shouldn't it be MGH because we're lifting? We're not lifting, we're pushing. So it's a horizontal distance. Let's crunch the numbers here. It's going to be 0.25 times 124 times 9.8 times 22. What do you got? William, what'd you get? You get something in the 6,000s, I believe.
6,684.
Give me the whole thing. 668
3.6
units. Work.
joules.
Yep. Why must that be wrong? Because it is wrong, technically. Why must that be wrong?
Has to be negative.
William, what?
Has to be negative.
Why would it have to be negative? What direction are we pushing? To the right? Sorry, what direction are we moving? To the right. But what direction is friction pushing? Left. They're in opposite directions. And what that really means is we're losing energy to friction. What would be a good way to show an energy loss? You just said the word. Yep. That's energy lost to heating up the floor. We put in 11,550 joules of work, but not all of that was on the box itself, making it speed up. A lot of that was just overcoming the friction between the box and the floor. We're heating up the floor. Same way as when you pulled your hand back, you heated up your hand. Matt, what's C want me to find?
In that work.
How would I figure that out? Well, I think that's going to be the total work that we put in, 11,550, minus the work that we lost due to friction. This is, don't do a minus minus. You could also have said plus negative, but I just think, oh, you know what? They're in opposite directions, bigger minus smaller. This is an energy loss, this is an energy gain. Think you're going to get something in the 4,000s? I think. What'd you get? 4866.4 joules. .4 joules. Then, if we were starting from rest, what was the mass? 126? 124? I can tell you that if we started from rest, we're now going 8.86 if I round off properly, meters per second. It's that quick. We haven't got there yet, but I'll show you how you can do that from the information that we have here. If you know how much work was done on an object, it's a very powerful tool. Work is force times distance. That's definition number 1. Force and distance have to be in the same direction. Force has to be constant. Work is also the area underneath the force versus distance graph. That's definition number 2. Your homework is try every question. But for